Morning, everyone. We are going to pick up today where we left off on Friday in our lesson on linearization or local linearity, or what's also called linear approximation. And in example 6, we're going to find the linear approximation to g of x equals the cube root of x at x equals 8. We will then use the linear approximation to approximate the value of the cube root of 10 and the cube root of 16 and compare the approximate values to the exact values. Find the error of our approximations. So the first thing we're going to do is find the second half of this ordered pair, the point where g is locally linear, where it has local linearization. Now, earlier in the year, we talked about if a function has local linearity at a point, that also means it's differentiable at that point. So what we can do is, first of all, evaluate g of 8. If I find g of 8, that's the cube root of 8. The cube root of 8 is 2. So my ordered pair is 8, 2. If I'm going to find the slope of my linearization equation, I first need to find the derivative of g. Well, g of x is also known as x to the 1/3 power. So the cube root of x is x to the 1/3. If I differentiate that, I get 1/3 x to the negative 2/3 using the power rule. And if I rewrite that so I don't have a negative exponent, I get 1/3 x to the positive 2/3. Or if we write it in radical form, x to the 2/3 is the cube root of x squared. Now what I need to do is find the slope at x equals 8. So I'm going to find g prime of 8. I get 1/3 cube root of 8 squared. 1/3 cube root of 64 equals 1/3 times the cube root of 64 is 4. I end up with 1/12 as my slope. So my linearization equation, L of x, is an approximation for f of x. So I'm going to say L of x equals g of x approximately, and that's 1/12 x minus 8 plus 2. Right, here's our linearization equation. It's an approximation for g of x. The linearization equation is 1/12 x minus 8 plus 2. Now, if we use that equation to approximate the cube root of 10 and the cube root of 16. So first of all, I'm going to find the actual values of the cube root of 10 and the cube root of 16. So I'm going to go to decimals here and figure out the cube root of 10. So the cube root of 10 is actually approximately 2.1544347. And the cube root of 16, I don't know why I put 12 in there, 16, is 2.5198421. Now what I'm going to do is I'm going to use our linearization equation. So I'm going to slide that out for a second. I'm going to use our linearization equation to find the approximations. So I'm going to say L of 10 is 1/2 10 minus 8 plus 2. 1/12 times 2 plus 2 is 1/6 plus 2, or 13/6. 2 could also be written as 12/6, and 12/6 plus 1/6 is 13/6. L of 16, the linearization at 16, is 1/12 16 minus 8 plus 2. 1/12 times 8 plus 2. 8/12 is going to be 2/3 plus 2. Or we could say 2/3 plus 2 is 2/3 plus 6/3, which is 8/3. Now, what we need to do, now that we have our actual values of cube root of 10 and cube root of 16, as well as the linearization approximations of L of 10 and L of 16, we have to figure out what our error is. So the amount of error is the difference between the actual value and the approximation. So when I find the error, 13.6, I gotta look at that. 13.6 is 2.166666667, so 2.16 repeating. The actual value of cube root of 10 is 2.15, and some other decimals after that. If you look at that, our approximation is higher than the actual value, meaning that it's an overestimate. So if I take 13.6 minus the cube root of 10, right, so 10 to the 1/3, the amount of error is 0.01223, so on. You could write out all the decimal places, but the amount of error for the first approximation, for the approximation for the cube root of 10, is 0.01223 ... And if we find the error for 16, the cube root of 16 is 2.519 up here, 2.5198421. Or I could take my approximation, which was 8/3, right? Clearly, our approximation, 8/3, is higher than the cube root of 10, or sorry, cube root of 16. So 16 to the 1/3. The amount of error would be 0.1468245, which, if you write both of these, sometimes error is written in scientific notation. So for the cube root of 10, we could rewrite 0.01223 as 1.223 times 10 to the negative 2. Right, I could move that decimal over 2 places. And here, for 0.146, I could write it as 1.468245. And I only had to move my decimal 1 place there, so it's 10 to the negative 1. So sometimes don't be surprised in other places, not necessarily in this homework assignment, but error can also be written in scientific notation. So I just wanted to review that with you. Okay, in the next example, we'll move on to example 7. It says, let f be a function that is differentiable for all real numbers. Remember, if the function is differentiable, it's also continuous. The table below gives the values of f of x and its derivative of f prime for selected values in the interval from -1 to 1. The function is concave up on the closed interval. So think about a function that's concave up. The tangent line is going to lie below the curve, which means that our linearization is going to be an underestimate of the actual value. Now back here, because our approximations were higher than the actual value, that means that the cube root of x at x equals 8 was concave down, right? So these approximations can help us determine the concavity of the function, right? So if I go to x equals 8 here, and I go to that point on the graph, 8, 2, you can see that the graph of the function x cubed, or the cube root of x, is concave down at 8, 2. If I were to sketch my linearization, which was 1/12 x minus 8 plus 2, you can see the linearization there. I'm going to change the color. You can see the linearization equation is on top of the curve. Therefore, the graph is concave down. G of x was concave down. And it also means that if we use the linearization equation, because it's on top of the function, it means that all of our estimates near the point 8, 2 are going to be overestimates. Now, because this function is concave up, it just means that the linearization equation will give us an underestimate for the true value of the function. So, it says write an equation of the line tangent to the graph of f of x where x is negative 0.6. So if we were going to find a linearization equation for f of x at x equals negative 0.6, first of all, we need to know what f prime of negative 0.6 is, because that's our slope. So we'll look right here, and our slope is going to be negative 2. So we're going to say negative 2x plus 0.6. X minus a negative 0.6 is x plus 0.6. And then we need to know what f of 0.6 is, so we know what the y coordinate is. Sorry, at negative 0.6 is negative 51. So that means we're going to say minus 51 on the end there. Now again, because the function f is concave up, this linearization equation, the tangent line is going to lie below the curve, meaning that this function, L of x, is going to give us a underestimate of the true value. So it says use this line, in part B, use this line to approximate the value of negative 0.5, which is really close to negative 0.6. Notice we have no information in the table about negative 0.5. So if I want to find L of negative 0.5, which is going to give us an approximation for f of negative 0.5, that's going to be negative 2 times negative 0.5 plus 0.6 minus 51. And if I take negative 2 times 0.1 minus 51, negative 2 times 0.1 is negative 0.2 minus 51 is approximately negative 51.2. Which makes sense because you can see what the y coordinates here are in the table. You can see the function is decreasing here, right, in this general area, right? So between negative 0.6 and negative 0.3, we can see the function is decreasing because the value of f of x is going down. And so it would make sense, it's not out of the realm of possibility that negative 0.5 would have a y coordinate of negative 51.2. If I put negative 0.5 into the table. Okay, so in letter C, we're asked to, is this approximation greater or less than the actual value of f of negative 0.5? Well, we don't know what f of negative 0.5 is. We don't know the actual value of it. But this is where they're asking you to understand that the fact that the function is concave up at the point, it's concave up on the closed interval from negative 1 to 1. So any x values from negative 1 to 1, when we use the linearization equation, we are going to have an underestimate. So I'm going to say because f of x is concave up on the interval from negative 1.0 to comma 1.0, let's see here, f of negative 0.5 will be I'm going to go back here quick. L of 0.5, negative 0.5, will be an underestimate of f of negative 0.5. F of negative 0.5 is the actual or true value. This right here is the approximation. So again, we can tell whether an approximation using our linearization equation will be an underestimate or an overestimate based on the concavity of the function. All right, moving on to example 8. We're asked to write the linear approximation equation for f of x at x equals negative 1, and then find an approximation for negative 1.2. So first of all, I need to find the second half of this ordered pair of this point. So I want to know what f of negative 1 is. That's 1 over negative 1 minus 1, or 1 over negative 2. Okay, so the ordered pair is negative 1 comma negative 1/2. And our linearization, in order to find our linearization equation, we need to know what f prime of x is. Well, 1 over x minus 1 could be written as 1 times x minus 1 to the power of negative 1, and then we could use the chain rule to differentiate. Or you may also use the quotient rule if you choose to do that. It will also give you the correct derivative. So I am actually going to use the chain rule, and I can use the power rule here. So 1 times negative 1 is negative 1 times parentheses x minus 1 to the power of negative 2 times the derivative of the inside, which is 1. The derivative of x minus 1 is just 1. So we have f prime of x equals, if I multiply negative 1 and 1, I get negative 1. And then x minus 1 to the negative 2 is going to be x minus 1 squared on bottom. Okay, I guess I could have here said negative 1 times 1 over x minus 1 squared. And if I multiply these fractions together, I do get negative 1 over x minus 1 squared. So f prime at negative 1 is going to be negative 1 over negative 1 minus 1 squared, which is negative 1 over negative 2 squared, which is negative 1/4. So my slope of my linearization equation is going to be negative 1/4. We know that L of x is going to be an approximation for f of x. So f of x is approximately negative 1/4 x plus 1. That's x minus a negative 1 minus 1/2. Okay, if I use the linearization equation then to approximate at negative 1.2, that's approximately f of negative 1.2 is equal to negative 1/4 negative 1.2 plus 1 minus 1/2. That's negative 1/4 times negative 0.2 is negative 2/10 or negative 1/5. Right, negative 0.2 is negative 2/10. If I reduce 2/10, that's 1/5, so negative 1/5. If I multiply those two together and subtract 1/2, I actually get 1/20 minus 1/2, or 1/20 minus 10/20, which is negative 9/20. So the approximation for f of negative 1.2 is f of negative 1.2 is approximately negative 9/20. Now it says to calculate the error of our approximation. Now if I look at the graph of f is 1 over x minus 1. So I'm going to take these other functions out here. Graph y equals 1 over x minus 1. And I'm going to go to the point x equals negative 1. Let's see what happens here. We're at negative 1 here. Right? We can see that the graph at negative 1 is concave down. The bend is downward. The function's bent downward. So the graph is concave down. If I graph my linearization equation, so I'm going to say y equals negative 1/4 x plus 1 minus 1/2, right? We can see that the linearization, the tangent line is above the curve, is on top of it. So therefore, anything we do with our linearization equation near that point is going to be an overestimate of the actual value. I can make that dotted. And when I find the exact value at, what do they want? Negative 1.2? The actual value of f of negative 1.2, f of negative 1.2 is negative 0.45 repeating. Our linearization equation, L of negative 1.2, is equal to, let's go here, make a table, negative 1.2 is just negative 0.45. Right, which is also, I believe, negative 9/20. Okay. As a fraction, negative 0.45 is negative 9/20. Now, if I find the error, our linearization is an overestimate. So if I find the difference between the actual, negative 0.45 repeating, minus negative 0.45, which was negative 9/20. If I subtract that, I wonder what, if I do negative 0.45454545454545, oh, 45. Let's see what the fraction is. Ooh, that's ugly. If I go and find, I just want to know if I can rewrite this actual value as a improper fraction. So negative 0.45 repeating, if I go back to the original function f at negative 1.2 is really 1 over negative 1.2 minus 1, which is 1 over negative 2.2, which is really, if I move this decimal over 1, I can move this decimal over 1 and say negative 10 over 22, which reduces to negative 5 over 11. Negative 5 over 11. Let's just make sure. Yep, that matches up. So really, when I'm finding the error, the actual value at negative 1.2 is negative 5 over 11. And our approximation is negative 9/20. So if I subtract those, I'm getting negative 5/11 plus 9/20. So I'm going to take that plus add 9/20. And our error is going to be equal to negative 0.00454545. And what that tells me, the fact that our error is negative, is that our function, right, our estimate is an overestimate because the actual value is less than the approximation by negative 0.00454545. Okay, now in the notes it tells you to take the absolute value of the error. Like they don't express error as a negative number, but I just wrote it this way so that to show you that if we take the actual minus the estimate, when you get a negative value, it just means that the estimate is greater than the actual value. So if we take the absolute value of that, the true error is the absolute value of that number that I just wrote right here. So if we take the absolute value of that, again, you could write it in scientific notation. You could say negative 4.54 times 10 to the negative third. So if I do take the absolute value of negative 0.0045, repeating, you get 0.0045. It's your true error. All right, our last example is going to be example 9. It says, given the implicit curve, x squared plus natural log of x over y equals 1. Write the linear approximation of the tangent line at x equals 1. So here's the thing. They give us the function. Because this is written implicitly rather than explicitly, it's not easy for me to find what my y coordinate is here. I would have to rewrite this explicitly to find that. However, they happen to give us the curve of the function, and they happen to show that the ordered pair is 1, 1. So I already know from the graph right here that y is equal to 1. And we know that the graph of the function is concave up because the blue tangent line that intersects at 1, 1 is below the curve. So we know that the function or the curve is concave up at 1, 1. So we want to write the linear approximation of the tangent line. We need to know what the derivative of this function is, or what dy over dx is. So if I differentiate with respect to x, x squared plus ln, the derivative with respect to x of ln of x over y, and differentiate with respect to x, the constant 1. So here I get 2x to the first times dx over dx. If I differentiate here, I get 1 over x over y times the derivative of the inside, which I need to use a quotient for that. So the quotient is low d high, so y times dx over dx minus high d low, which is dy over dx, and all over the square below, which is y squared, and on the other side I get 0 when I differentiate 1. So I actually end up with 2x to the first is just 2x, dx over dx is just 1. If I take 1 over x over y, that's just really 1 times y over x, times, and then inside the parenthesis here, this is just y times 1, which is y, minus x times dy over dx over x squared equals, over y squared equals 0. So I end up with, I'm going to go down here below, I get 2x plus y over x times y minus x times dy over dx over y squared equals 0. So first of all, I'm going to move the 2x to the other side. I get y over x times y minus x times dy over dx over y squared. The 2x moves to the other side, so that's negative 2x. I'm going to get rid of the y. I'm going to divide here by y over x. If I divide by y over x, that's the same as multiplying by the reciprocal. So I'm left with y minus x times dy over dx over y squared. And here This is the same as saying negative 2x times x over y. Multiplying by the reciprocal, I get y minus x times dy over dx over y squared equals negative 2x squared over y. Now here I have a proportion. I think we could probably cross multiply if we wanted to. We don't have to. I think you could cross multiply and say that the cross products are diagonal products are equal. I think I'm going to take the approach that I'm going to multiply both sides by y squared to get rid of the denominator on the left side. That leaves me with y minus x times dy over dx equals, when I multiply by y squared here, I'm going to get negative 2x squared y squared over y. And one of the y's will cancel on top and bottom, which will leave me y to the first on top. So I get y minus x times dy over dx equals negative 2x squared y. I'm going to now move this y to the other side, so I'm going to subtract y on both sides. That gives me negative x times dy over dx equals negative 2x squared y minus y. And I'm going to divide both sides by negative x then to get dy over dx equals negative 2x squared y minus y all over negative x. Now, some people might ask about canceling out an x here and here. You cannot because you don't have an x in this term, and you still need x. You still need negative x to be the denominator for that second term of minus y. Okay, so that's our derivative. If you wanted to rewrite it, you could as negative 2x. Actually, it'd be positive. It'd be positive 2xy plus y over x. If you wanted to simplify, if you wanted to break up the fractions, you could divide this term by negative x and divide this term by negative x. Both terms on top are negative. The denominator is negative, so those negatives would actually cancel out. So you could write it like this, or you could write it like this. Either of those are the same thing. Okay, so we have our derivative. I think I'm going to use this one when I evaluate. That's our derivative. We want to know what our derivative is at x equals 1. So we can find the slope of our tangent line or linear approximation. So, and we know that at x equals 1, y is also equal to 1. So 2 times 1 times 1 plus 1 over 1. And the reason why I know x and y are 1 is because the point of local linearization is at 1, 1. So we have 2 times 1, which is 2. 1 over 1 is 1. So then we get a slope of 3. The slope of our linearization is going to be 3. So when I write my linearization up here, I'm going to say L of x is an approximation. Actually, no, L of x is going to be equal to, we aren't given the name of the function as f or g or anything like that. So I can just say my linearization is 3 times x minus 1 plus 1. I'm using the ordered pair 1, 1. And we evaluated the derivative at 1, 1, and we got a slope of 3. Okay, so from there, that's part A. Use the tangent line to the curve at x equals 1. Find the number k such that the point 1.25 k is on the curve. So for part B, we're going to use the linearization. We're going to say what is L of 1.25, and if I put that into our linearization, we get L of 1.25 equal to 3 times 0.25 plus 1. Well, 1/4 of 3 is 3/4, so 3/4 plus 1 is going to be 3/4 plus 4/4 or 7/4. Or if you want to give the approximate value of that or the decimal value of that, that's 1 3/4. So the value of K, when I plug in 1.25, the value of K is 1.75. Using the linearization, we'd get 1.75. So that probably makes sense based on the graph because this is 1, this is 1.5. So it seems reasonable that 1.75 would be right there. Now, what they did to find the actual value of 1.25, this is an approximation using our linearization equation. But they did actually explicitly write this curve. So if I were to solve that for y, if I take x squared plus natural log of x over y, x squared plus natural log of x over y, what was it, equals 1. If I solve this for y, I can do that. I'm going to subtract x squared on both sides. I get natural log of x over y equals 1 minus x squared. Now I can rewrite this because natural log is base e. I can rewrite this in exponential form instead of log form. To do that, I can say e to the power of 1 minus x squared is equal to x over y. And if I multiply both sides by y, I get y times e to the 1 minus x squared equals x. And then I can just divide x by e to the power of 1 minus x squared. Now, that's the explicit form. Now, if I, in part C, want to calculate the error of our approximation, I need to know what the actual value of x equaling 1.25. Our approximation was 1.75. If I go and find the actual value, I can plug in 1.25 for x. So 1.25 over e to the 1 minus 1.25 squared. So I'm going to take my explicit form here, plug in 1.25 for x, square 1.25. We get 1.25 divided by e to the power of 1 minus 1.25 to the second power. And it looks like our answer there, the actual value is 2.1938183212. Now that's quite a bit of an error because remember our estimate was 1.75. Okay, so if we're going to calculate the error, this is the answer for part C. The error is going to be f of 1.25 the actual minus the approximate answer, which is using our linearization equation. We get 2.1938183212 minus 1.75, and we get 0.443818 ... So 3212. Okay, that is the amount of error. And that's because the actual value and our estimate from our linearization, the actual is greater than the estimate, which tells me that if I graph that function, since the estimate is an underestimate, we know that that function, if we graph that implicit function, or even if we graph it explicitly, we know that it's concave up because our estimate is an underestimate for the actual value. It's off by almost a half a unit, not quite. So yeah, our amount of error is 0.443818. So you could write that in scientific notation, if I round to the nearest hundredth, 4.44 times 10 to the negative 1. Right, we just move the decimal place over 1. It would be 4.44 if I round to the nearest third decimal place. And then since we moved our decimal 1 place to the right, our exponent would be negative 1. All right, that is it. You are free to work on your homework assignment. I will be collecting the linearization homework assignment on Wednesday this week. So you have the rest of today and tomorrow of class to work on the linearization assignment. All right, I will see you guys tomorrow.